Yes, in the previous session, so MBA search tree, why we are discussing. So from that only MBA search tree, we have the other topic that B trees and B plus trees. We'll see that later. Okay, and that's why we are discussing MBA search trees. I told in the previous section, and these are the rules I told that in the previous section. 4 rules. Okay, so we'll see in the example. Now let's see the example. Suppose let us say this is the MBA search trees. Here the order is 5, maximum 5. Order maybe maximum 5 means it have maybe uh, yes, maybe this node have at most 5 child nodes. Here 3 is there. In this case it is 3 is there. At most have 5 child nodes. M equal to 5 order means. Okay. You see this. The rule, as per the rule, first rule we'll see. First of all, first rule. For some integer m known as the order of the tree, each node has at most m child nodes. Yes. Here the a node may be represented like this: a naught, a k1, a1 is like this, which the key values should be less than or equal to m minus 1, and the same way a pointers also less than or equal to m minus 1. Okay. I told you that key values here m equal to 5. Key values are nothing but this is the key values. First key value 18, second one 44, 76, and 198. These are the key values. Okay, which is key values. Number of key values is compulsory less than m. That means less than or equal to m minus 1. So that is satisfied. This is the pointers. This is the pointers. Pointers also you see. Pointers also less than this pointer less than m. That means less than or equal to m minus 1. So 3 pointers only here it is there. Okay, but m is 5 here, pointers 3. Okay, here is key values are 4 and here m is 5. Okay, this rule is satisfied. This same thing rule is applicable for the internal nodes also. Internal nodes, not only the root node. Okay, in the internal nodes also at most m childs. This internal node has at most m childs. M child means after 5 m minus 5, but at most means that it contain 1 or 2 or 3 or 4 or 5. For child nodes it is 0. Okay, so here is 1 is enough. Yes, 1 is there. This is the tree. So here also 2 key values, which is less than or equal to m minus 1. That means less than or equal to 4. M minus 1 means 4. Here also pointer 1 less than or equal to 4. Okay, yes. Here is 3 key values. Key values less than or equal to 4. And pointers 2 less than or equal to 2 pointers are there. 2 pointers less than or equal to 4. Okay, in the same way here 1 key value 1 less than or equal to 4 and pointer also 1 less than or equal to 4. Yes, fine. Okay, 1 minute. Something it is getting. Yes. Notation we'll see. So this is in the same way every node is following the properties. Okay, the first rule, this is the first rules. Okay, I told you that here, see here key values is 4 or not 5. If it is 5 means it come as a down based on the rule. So here is 3. If here the pointers are null, all are null. So 0 0 here 0 0 here pointer 1. Here this is 2 pointers and this is 1 pointer. Here this 3 pointers. Okay, yes. So this is first rule. Second rule we'll see. Second rule we'll see. Yes, second rule. If the node has k child nodes where k less than or equal to m, okay, then the node can have only k minus 1 keys. K minus 1 keys. I'll tell you that number of nodes for each child may be m, as at most m childs. So keys of for that node have k minus 1. K minus 1. Yes, You'll see if k childs are there for that node key values are k minus 1. Okay. Yes. Suppose such that ki less than ki plus 1. See, it is a non-decreasing order. The values are in the non-decreasing order in this in the node and the subtrees also. You see, that is the second rule we'll see here. In this example, in this, I told you that. So in this case, having k values 4, but this is only one example only. Here you see childs are, suppose childs are 3 only is there. If I want to attach, I can attach the fourth child and fifth one also. Maximum, suppose maximum capacity is 5 now. So for that 5, number of key values should be, suppose k is k children are there. In this case, 3 only is there. But totally 5 can add it. We can add 5 childs. Okay, here 3 only is there. So that whereas the number of keys for this node should not equal to equal or greater than number of childs. Key values, keys, number of keys is 4 here. Okay, it is this is should not greater than m at most child nodes. That means here only 3 is there. We can while inserting we can show that also. Okay, totally 5 out of 5 actually, but here we're only showing 3. Okay, should not exceed the m. Should not exceed the m. Okay. In the same way, here also applicable. Even the child is 1 is there, but maximum is 5. Here only we can key value should be 4 only. Maximum should be 4. Okay, here also key value should be 4 only. Childs will be 5. Yes. Here also. Yes. Here also same thing. We have this rule. Suppose if I want to, when you will understand, suppose if I want to insert another node, so that node will not insert here, not added as a key. Maybe depend upon the rule, maybe this side or this side or this side. And this is the thing, because at most for m minus 1, okay, keys and with m childs. Okay, at most m childs. So this is the 4. Maybe maximum 5 childs should be there. Here also, if maximum is 4 and childs will be 5. 4 and 5. Here also should can insert 4 keys and 5 childs we can add. Okay, this is not complete tree. So see here, these key values are all in non-decreasing order. In each node, key values k1, k2, k3, k4 are non-decreasing order. And this is here also non-decreasing order, 7, 12. Yes, increasing order, that meaning. So that is the rule we followed. Not only the main node, subtrees also same rule we following. And now the third one. So for each node, these are the key and pointers. All the key values in the subtree pointed to by ai are less than the key ki plus 1, 0 less than or equal to I less than or equal to m minus 2, and all the keys in the subtree pointed to by a m minus 1 are greater than km minus 1. How this is, what is this point? I will explain now. See here, whatever the key value here, key value is k1. Suppose let us say ki, let us say 18 as a ki. Less than this key value 18, less than, I told you that less than, they come this side. Suppose if I want to insert 12 as a, add as a left child. Okay. If I insert any 7 means as a 7 is also a left child. I can attach a before the 12. Okay. Suppose while inserting, first of all, when constructing trees, when constructing this tree, first I insert the 18 after 44, 76, 198. So these are the first 4 values I inserted. After inserting this first 4, the m address 5 na. So I want to insert 7 means, suppose 7. 7 means it goes to this side. Because 7 is less than 18, should be less than 18. Because here maximum capacity reached, so left side we need to attach. Suppose this time 12 I want to insert. So this should be less than 18 means, so same thing. So I can add 7 after 7, 12. In the same way, this time I want to insert 80. 80 means, we'll see here. See here. Between this range 18 to 44, no, 80 is not present in between this range. If it between this range, suppose if it is instead of 80, 30 is there, here I can insert. By using this pointer, I can insert. Okay, if 30 is there, then I can insert, but he is not there, 80. So 44 to 76, no. And 76 to 180, 198, yes. So between this range, 80 is present in between 76 to 198. So in down this pointer, the pointer which between these two, 76 and 198. So this here I can attach as another subtree, 80. Child, another child, 80. Suppose next time I want to insert 92. 92 also not between this range. For searching, you have to see. And not in this between this range. And 76, yes, between this range only. We already inserted here 80, so I can insert 92. 92 here. Suppose this time 141. So same thing. So the 141 also between this range. Yes, I can insert. Okay. Suppose next time I want to insert the 262. So here 262 not between this two range, not less than this 18, and not between this range, and here also not between this. It is 262 is greater than 198. That meaning I need to attach as right child. I need to attach as okay. Yes, fine. As a tree, subtree, like a subtree this side. Okay. For one node we can like this add it. Two pointers like this. Okay, that means the total number of keys 3 means pointers will be 4 almost. 3 means 2 means 3. Okay, but here only using less. Using pointers are less. Okay, let's see. So next time I want to insert 8. Suppose 8. A come here. So 8 comes between this range 7 and 12. So I can insert here 8. Next time I want to insert 10 means 7 and 12 between this range 10 is there. So I can insert here. Okay, so like this. Yes, this is about. So see here, suppose 77. 77 is less than 80. So I can attach here. Okay. So whereas 77 is greater than 44, 77 is between 77. So 77 is where it is ranges 76 to 198 between this range it is there. So again we are checking here. 70 not between it is less than 80, so I can go this side, so I can attach as a left child like this. Same way this one also attaching like this, same way. 148 is which is greater than 148, 151, 172, 196. These are all the between the range that is 141 to 198. Okay, 141 to 198. So that's why this side only. After 141 only we need to attach. Okay. Suppose this time I want to insert I want to insert 145. For example, 145. Where will we insert? So 145 between this range. Again, I'm searching 145 is greater than this one. This side I will come, and 145 is less than 148. But here maximum number of nodes reach 4 is reach. Okay, so that's why I need to attach to this side as a. Suppose if I want to insert, I will write that one diagram also. So maybe 141. So 141. If I want to insert say 145, 145. Okay, if I want to insert 145. Okay. So the node and pointers, 2 pointers like this we can add first, but which is null, Okay, if I want to insert, so this is about. Okay, so this is about the M-way search trees, how we are implementing. And fourth point, I told you that M-way search tree, that also M-way search tree, subtrees of particular area. Suppose this is the pointer. For this also, this subtree is also M base search trees. This subtree also, this one also M base search trees. This one, for this particular point, this subtree is also M base search trees. For this one also, this is a M base search trees. The subtrees are also becomes a M base search tree. That is the fourth point. Okay. First point I told you that. First point I told you that all at most m childs, each node have at most m childs, and key value should be less than m. Yes, fine. And pointers also should be less than m. Yes, fine. And maybe in suppose number of childrens is k means may here key value is k minus 1. Okay. This is only when we are reaching the maximum limit. Here it is only showing 3. We can add 4, maximum 5 we can add childs, but key values is 4 only. Yes, that is satisfied. So this is applicable for recursively for the internal nodes also. Okay. So after the next one, next point, next rule is what I told that. So all the key values non-decreasing order. Yes, all are in non-decreasing order, and also uh, how we are placing. So say here, suppose in this example, less than ki minus 1 should be the left side, less than that should be left child. So and also maybe something ki, suppose let us say ki between this range, it is ki minus 1 and ki plus 1. Between this range means I can maybe attach to the this side like this. The ranges between these ranges, if you want to set any new one, we can attach as a childs. Okay, I told you that. Yes, this is the rule, and all the subtrees are m way search trees. Okay, this is about. Suppose look for 77 searching operation. Let's see. Look for 77. Yes, we can look. So which is greater than? Yes, which is less than? So yes, it is already there. Yes, searching is very easy, but now let's see insertion also. Let's see insertion. Suppose this is the tree now at present I constructed. So I want to insert the new one, 6. Yes, 6 is less than 18. So this side I need to go. So this side 6 is not between this 7 and 12. So it is less than 7. Less than 7. So here maximum number of nodes not reached. Okay, key values. Maximum 4 now. So we can insert here 6. See, after inserting 6, what happened? Yes, see this side. 6 will come this side. Because maximum 4 I can attach in that node. Okay, that key values. And I want to insert 146. You see here 146. How will I am inserting? You see here this count 146. Yes, 146 greater than yes, greater than this 141. Yes. Still that 146 is less than 148. So I can attach as because here maximum 4 is reached. We reached 4 maximum. If it is not there, maybe yes. If it is not there, if it is not there, 146 I can attach here only. If it is not there, I can attach 146 here only. Because maximum 6 I need to reach, but it is there now, so that's why I need to search down also 146. Okay. Yes. So that is. So this is suppose like this as a child, right left pointer, which is less than 148. Yes. So this is insertion. Deletion is we need to search between the key between the pointers. AI k should be in the AI aj pointers. Yes. I want to delete. Suppose in deletion operation. This is suppose delete operation in the m-base search tree. See here. M-base search tree is delete operation. 151 I want to delete. Yes, if it is there or not. Yes, 151 is there. Yes, it is there. So after deleting, nothing will be changed. After 148, 172, 186 is there. So suppose, yes. Yes, same. See here, 151 is deleted. So 148 and between this 151 is deleted already. Yes, deleted. Yes. Okay, very simple. And how I am deleting by searching all 151. See, between this range. Yes, you see the previous step. between this range, yes. This meaning here I need to come this side. Between this range, yes, this side I will come. 151 again is greater than 141. So I need to go this left subtree, left child, not subtree, left child. Again here I'm checking 151 is yes, it is found here. Then I will delete this one. Then I will delete this one. Yes. After deleting, this is the thing. Yes, this is the node with the key values. Yes, that is, and that is the delete operation. Suppose if I want to delete operation one node. Suppose I want to delete the 262. What happens? See, 262 I want to delete. Yes, simple. If I want to delete this with one child, 262 I want to make it as 272 as a child. I can take from here. I can insert here. I can replace here. Instead of 262, I can replace with 272. You see here. Yes, happen. After deleting 262, 272 as a child to the this root node. Okay, right child. So in the same way, I want to delete the 12 means yes, we can easily delete 7 is there still. Okay, 7 is there. If I want to delete 7 also, 8 will become as a left child. See this one. 12, yes, after deleting 12, 7, 10 only is there. Yes, huh? Yes. After deleting, yeah. Okay. Here, yes. After deleting here, every time when you are deleting, we need to replace. We need to replace with the child node key values. Yes. After deleting 12, I want to insert 7 will 10 will come here. So when you are deleting operation in the internal node, we can replace with the key value from the child nodes. Okay. So here also same thing happen. Yes. Fine. So 10 come here. Yes. Yes. Fine. If I want to delete, uh, yes. Fine. Okay. This is about. So this is about the delete operation while inserting and while deleting. What happened, and also searching also. So in the MBA search trees. This is about the MBA search trees. Uh, in the next section, I want to discuss about B trees and B plus trees. This is important topic. Okay. So why we require B trees and B plus trees now in order to access memory efficiently. So these B trees and B plus trees are used in the database management system, database DBMS file. While searching particular record, deleting and inserting, we can from the database we can do efficiently than AVL and red black trees. That's why it is important. B trees. Okay. So this B tree is nothing but extended M-based search trees by adding the addition of external nodes which are null pointers, which having null pointers. MBA tree is nothing but this is a B tree is nothing but MBA search tree with external nodes. I can say it as with external nodes. You'll see that in next class the terminology about B trees. So the B trees terminology and examples also, and insert and delete operations, and also B plus trees also. Okay. So in this section, I'm going to close this. So today now in this class, I covered in this section I uh, covered the MBS trees with the rules. Yes, MBS history with rules, how you are you followed or not. Yes, by constructing and look finding, searching for particular sounds on how we can do. To insert a 6 node, how we can do, we'll discuss 146, we discuss insert operations, and also we discussed about delete operations, how we are deleting. We every time we are replacing with uh, the current node values replaced with the child node key values. Yes. Okay. Yes. So that is we discuss delete operations and 262 in the same way. To yes, delete 12 also over. So this is and why we are using B trees I discussed in this section. So in next section, discuss about B trees and B plus trees in detail about insert, delete operations, how we are constructing. Okay, what are the rules we follow in B trees and B plus trees? Okay, so from this, I want to close this section.